Ever wondered how trees can be more than just part of a nature? What if I told you that in the world of algorithms, trees can teach us something about balance? Today we are diving into a fascinating even tree challenge. Imagine you are a forest ranger trying to keep your trees population evenly split. How many cuts do you need to make to ensure every subtree has an even number of nodes? Stick around because we are about to uncover the secrets of tree structures and some mind-blending problem solving. All right, let's dive into the approach for solving this problem step by step. Imagine you are sitting together, mapping this out on a whiteboard, and I'm guiding you to the logic behind the code. First up, we need to understand that we are working with a tree structure. Trees are a special kind of graph where there are no cycles and they can connect nodes in a hierarchical manner. Our goal here is to find edges we can remove from this tree such that resulting subtrees has an even number of nodes. Sounds straightforward, right? But the challenge lies in figuring out how to navigate this structure effectively. Step 1, setting up the tree. We start by creating an adjacency list. This is essentially a way to represent the tree in a format that's easy to work with. Each node will have a list of its connected nodes. This step is crucial because it allows us to quickly access which nodes are connected to which. We'll use a dictionary for this, where each key is a node and the value is a list of its children. This setup helps us keep track of the tree structure as we process it. Step 2, gathering input. Next, we need to read the input, specifically the number of nodes and edges. This is the foundation of our tree. With this information, we can start building our adjacency list. Each connect edge are nodes, and for each edge we'll make sure to add both nodes to each other's list. This bidirectional connection is what gives us the picture of the tree. Step 3, building the tree. As we loop through the edges provided in the input, we populate our adjacency list. If the node doesn't exist in our dictionary yet, we create a new entry for it. This is where we construct the entire tree structure that we'll be navigating later on. Step 4, traversing the tree. Now that we are ready to traverse the tree, we'll use a depth first search approach starting from a designated root node, typically node 1 in this problem. DFS is perfect for this task because it allows us to explore each branch of the tree deeply before backtracing. Step 5, counting nodes and removable edges. As we perform our DFS, we'll keep track of the size of each subtree. The key insight here is understanding that if a tree has an even number of nodes, we can safely remove the edge connecting to its parent without violating our constraints. This will be our main criterion for counting removable edges. Step 6, the DFS function inside our DFS. So inside our DFS function, we first mark the current node as visited, and to avoid cycles, we initialize a counter for the number of nodes in this subtree starting by 1 because we are currently at this node. Step 7, exploring children. Next, we loop through each adjacency node. These are the children of the current node. For each child, we check if it has already been visited. If not, we recursively call our DFS, which will return the size of the child subtree. Step 8, evaluating subtree sizes. Here's where the magic happens. After getting the size of a child subtree, we check if it's even. If it is, we can increment our count of removable edges. This is a pivotal point of our logic because it directly ties back to our goal. If the size is odd, we simply add the child size to our current structure size. By the time we finish our DFS, we have traversed the entire tree, counted the size of all subtrees, and determined how many edges we can remove while maintaining each size subtree. Finally, we output the total count of these removable edges. And there you have it. We have laid out a clear path from understanding the tree structure to counting the removable edges. With this logical foundation, all right, folks, let's quickly recap what we have covered today in our deep dive into solving the HackerRank problem on even trees. We started by constructing an adjacency list to represent the tree structure based on the input edges. Then we implemented a DFS, depth first search algorithm, to explore the tree and count the removable edges. The key takeaway here is how we leverage the subtree sizes to determine if an edge can be removed while ensuring the remaining trees still have an even number of nodes. Remember, the power of DFS is in traversing trees structure cannot be overstated. If you've enjoyed this walkthrough and found it helpful, make sure to hit that like button and subscribe for more coding insights and solutions. We have some exciting content lined up next, and we'll be tackling graph algorithms and exploring more complex tree structures. So stay tuned and keep coding.